guys, it's your favorite teacher, Godson, and you know what it is. This is Wits Lounge, learning made easy. Now, today we are going to be studying a new concept, and that is collision theory and energy profile diagram. Yes, the two of them are actually related, so get strapped on as we get into this class. Now, before we get into studying, if you have not subscribed to my video, I beg you, go and subscribe. Thank you very much. So, what are we trying to say about collision theory? First of all, collision theory was postulated by Mr. Arrhenius, and his theory is simply describing how reactions would occur or how reactions actually start. Before we get there, I'd like to say this. Now, collision implies, what just happened here? When two things hit each other, that's collision. So when you say things are colliding, it means that they're actually bumping into each other. That's collision. And you see examples, for instance, in the American football where they're like, hut, and you get what I'm saying. So the American football is where you find a lot of head collisions. But we're not talking about head collisions in this case. We are trying to talk about chemistry. And what am I trying to say? Collision theory, as postulated by Arrhenius, states that for a reaction to occur, the reactant particles must collide. I take it again. Collision theory simply states that for a reaction to occur, the reactant particles must collide. Now, having said this, it still doesn't imply that every collision will lead to a reaction. Just have this in mind. The fact that reactions start by collision doesn't mean that every time there's a collision, there will be a reaction. For instance, let's use marriage as an analogy. We know what marriage is, when the ring is put on the lady's finger. I don't know what finger, but yes, putting a ring on the lady's finger. Now, say, if you are going to talk about marriage, for every marriage to start, there has to be the first point where the guy, steps into the place, all cool, and then looks at the lady and is like, my lady, I got you, because you are the right amount of sunshine to my brown, cloudy sky. And then the lady's all like, oh my God, that's so cute and stuff. Yeah, that sounds lame, but the point is this. The first part that would lead to marriage is that the guy and the girl would have to come together and be like, yo, what's up and stuff. There has to be a first point of contact. Now, the fact that that guy talks to that girl, in Nigeria we call it Ewatiti, you get. The fact that the guy talks to the girl does not imply that there would be marriage or even a relationship. That's the same thing with atoms. The fact that they bump into each other and keep bumping does not mean that reactions will occur. So what then do we have to say about this? How are we going to bring about a reaction? Just like in the case of marriage, there are certain things that a lady and a guy requires from his spouse before they get into that marriage. There are certain qualities they're looking out for. For instance, some ladies will be like, once he got the dough and he has, that fine body, the guy is good to go. That's what some ladies would say. Some people are like, oh my God, once he's caring. Those things are requirements that would make her consider marriage. The fact that they talked does not mean that they're going to get married. There are certain requirements she has, and once those requirements are met, that guy is definitely putting that ring on that finger, and you have marriage. That same thing happens with respect to atoms, because I believe that atoms actually sometimes act like humans. The fact that they are colliding does not mean they are going to react. There are specific energy requirements from each of the colliding atoms that must be met before a reaction occurs. Yes, that's how they are. So, with that said, I'm just trying to say that collision theory, yes, states that reactions start by collision, but not every collision leads to a reaction. Just like not every contact or not every beautiful poem read to a girl will lead to putting a ringer on that girl's finger. A ringer on that girl's finger. Let's just continue. Now, my point is this. Every reaction that occurs starts with collision. But for that collision to lead to a reaction, there is a minimum requirement. That minimum requirement is what we call activation energy. We'll get to that and understand this concept. But let's look at the diagram I was trying to relate. You have your atom and atom. They collide. But the fact that they collided doesn't mean you're going to have a product, that is reaction. A reaction. Oh, sorry. Let's rewrite that. Reaction. For you to have a reaction, there's a minimum energy requirement, and that is activation energy. I told you, the guy and the girl, they're all smiley and fine. I don't know how to draw. So they chat. Before you get to marriage, there are so many steps. The girl has to know the guy has to know the girl, and then they have to meet their minimum requirements, which might be love. You get that, and so many other things. But the point about it is this: before you transit from colliding to get to the reaction, or transit from talking to other to get to marry, there are specific energy requirements. And in this case, for reactants, it is referred to as activation energy. So the activation energy is defined as the minimum amount of energy required by colliding particles for a reaction to occur. Yes, and that's that. Activation energy is the minimum amount of energy required by colliding particles for a reaction to occur. So, with that said, I would like to describe activation energy with respect to energy profile diagram. So we're going to take a pause on understanding activation energy right there. But have this in mind. Once two colliding particles have the required activation energy, boom, reaction occurs and product is formed. So let's continue. We are done with understanding the concept of collision theory and the fact that colliding particles do not always lead to reaction, and why they don't always lead to reaction. The reason is simple. As I said, once the colliding particles do not meet the energy requirements, there would be no reaction. So let's get to understand the whole process using the energy profile diagram. Profile diagram. Now, as we all know, when you talk about the energy profile diagram, it simply describes something: the relationship between the energy of a reaction and the reaction pathway. We'll get to understand this more. Before we get to understand it more with the diagram, we will need to understand the concept or certain terms with respect to this. We'll start with the first one. Every reaction that occurs can either be endothermic or exothermic. So we'll need to understand certain terms with respect to this study. So let's start with terms related. The terms related to the energy profile diagram. Number one is enthalpy change. Now, enthalpy change is described as the difference in the heat of the product and the heat of the reactant. It's more or less described as the heat content of a particular reaction. So how do you derive enthalpy change? Enthalpy change is derived by the difference between the heat of the product and the heat of a reactant. We will get to discuss enthalpy and its full concept when we get to study thermochemistry. But so, with this said, enthalpy change is first of all represented by delta H, and it is equals heat of product minus heat of reactant. So once you have the H is equals heat of product minus heat of reactant. Quite simple, right? So put that down. Enthalpy change equals heat of product minus heat of reactant. Now, having understood the concept of enthalpy change, there are two major forms of enthalpy change: positive enthalpy and negative enthalpy. We'll start with the positive enthalpy. First of all, the positive enthalpy occurs when you have an endothermic reaction. So that means anytime you have an endothermic reaction, the enthalpy change is positive. So we start with the first one, A, endothermic reaction. So what is an endothermic reaction? An endothermic reaction is a reaction which requires absorption of heat to the system. I take it again. An endothermic reaction is a reaction which requires absorption of heat to the system. In this type of reaction, you will find out that the heat or the energy of the surrounding reduces. The temperature of the surrounding reduces, and because of that, that is referred to as an endothermic reaction. Examples of your endothermic reaction is, for instance, your vaporization process. You bring something like your methylated spirit and you rub it on your finger or your hand. You notice that as the methylated spirit is vaporizing, the temperature of your hand is cooling. What is it trying to tell you? Endothermic. Endothermic causes a reduction in the temperature of the surrounding. So exactly that. Endothermic reactions are reactions which involve absorption of heat to the system. Having mentioned that, we described that endothermic reaction must have an enthalpy change which is always positive. Every endothermic reaction has a positive enthalpy. So have this in mind, that once you are dealing with an endothermic reaction, the enthalpy change is always positive. Now, with this mentioned, you would have dH is equals heat of product minus heat of reactant. For a reaction to be endothermic, it must have a positive enthalpy. And if you are going to have a positive enthalpy, the heat of product must always be greater than the heat of reactant. Put that down. For a reaction to be endothermic, enthalpy change must be positive. And if enthalpy change must be positive, the heat of the product must always be greater than the heat of the reactant. So H of P must always be greater than H of R. See what I mean? If we are going to have two values, let's say the heat of product is 7 kilojoules and that of the reactant is 5. H of P equals 7. H of R is equals 5. What are we going to get from this? The H is going to be equals 7 minus 5, which is equals plus 2. Positive enthalpy. So for you to have an endothermic reaction whose enthalpy change is positive, the heat of product must be greater than the heat of reactant. Okay, if you happen to do it the other way, where the heat of product is less, you're going to have 5 minus 7, and that's going to give you a negative value, which is not an endothermic process. So have this in mind. A positive enthalpy reaction is an endothermic reaction. And for that reaction, which is endothermic, to have a positive enthalpy, the heat of product must be greater than the heat of reactant. This is very important to helping us understand how to put up the energy profile diagram. So even if you forget every other thing, let this keep ringing in your head. For a reaction to have a positive enthalpy, the heat of product must be greater than the heat of reactant. Thank you very much. That is what we describe when we talk about an endothermic process. Now, the second form of enthalpy change is a negative enthalpy. And the negative enthalpy occurs in exothermic reactions. So what is an exothermic reaction? An exothermic reaction is a reaction which involves liberation of heat from the system. So heat is released from the system to the surrounding. The implication of an exothermic reaction is once that happens, you will notice that the surrounding will become hotter. Yes, that is the characteristic of an exothermic reaction. It releases heat to the surrounding. For instance, when you are performing a neutralization reaction, which is a reaction between an acid and a base, what happens? You will notice that the container becomes hot, especially when you are dealing with concentrated solutions. So that process is exothermic. Any reaction which involves the release or liberation of heat to the surrounding is referred to as an exothermic reaction. And yes, every exothermic reaction has a negative enthalpy. So let's take this out of the board. We are done with the endothermic. Let's understand the exothermic. So what am I trying to say? That once we are dealing with the exothermic, that's B, exothermic, it is a reaction which involves liberation of the heat from the system to the surrounding. And in those reactions, enthalpy change is always negative. I give you an example of an exothermic process, neutralization reaction. Good. We are not discussing that fully here. We'll talk about that when we are describing thermochemistry. But for now, we are going to be taking a brief understanding or brief description so that we'll be able to understand how to draw our energy profile diagram. Now, having mentioned that, write this down. For a chemical reaction to be exothermic, delta H must be negative. And if delta H, which is the change in enthalpy, is going to be negative, the heat of reactant will be greater than the heat of product. I take it again. For a reaction to have a negative enthalpy, the heat of reactant must be greater than the heat of product. Once that happens, the enthalpy change must be negative. I take it again. For a reaction to have a negative enthalpy, the heat of reactant must be greater than the heat of product. Now, this understanding would help us when we get to drawing our energy profile diagram. So please don't take these things for granted. Every single note that you should take note of, please put it down. I take it again. For endothermic, the heat of product will be greater than the heat of reactant. But for exothermic, with a negative enthalpy, the heat of reactant has to be greater than the heat of product. Thank you very much. With this said, we go to the next term for this particular diagram. And that next term is the activated complex. What is the activated complex? Now remember I told you guys that we are going to be using a marriage analogy to describe collision theory. So I'm going to be talking a lot about marriage and collision theory intertwined. Don't get confused. We talked about collision and we said for any reaction to occur, the particles that are reacting must collide at first. And we said that for any marriage to occur, those that are involved must have a first contact where they, get to capture one another's attention. But besides that, the fact that they are colliding does not mean that there will be a reaction. Something has to be there for a reaction to occur between colliding particles. And we have described that as the activation energy. Same thing. Something has to happen between them. The requirements must be met before the two couples get together and then become married. Now, before marriage occurs, the guy has to propose to the lady, or the other way around. There is a proposal, and then they turn from just being normal people dating to the fiancé. So have this in mind, that before it starts with contact where they talk, and after contact they start dating, they become maybe a boyfriend and a girlfriend. After that, the guy tends to propose most of the times. Now, at the point of proposal, it's now a different ball game. Once you turn into a fiancé, you are no more just a girlfriend. You are yet or about to get married. Now, that same thing happens with respect to collision theory. After they collide, energy is being absorbed, and once that required energy is gotten, they convert from just dating or just talking to a transient state known as activated complex. So it's just like marriage. You talk, you date, and after dating, you get into a transient state. Immediately after the fiancé level, you are getting married. That's how it works, even though not all of them work that way. But just have this in mind. Immediately after the fiancé, automatically you are getting what? Married. Because after you become a fiancé of somebody, the next thing is to put a ring on that finger. Yes, put a ring on that finger. But that's not what we're talking about. We are talking about collision. They keep colliding, they get the activation energy, but before the reaction occurs, there is a state, a transient state, which is not the product. It is just a transient state showing that we have gotten everything required for this reaction to start. That transient state is referred to as activated complex. So you can put this down. Activated complex is defined as a transient state in which reactants are when the activation energy is completely gotten. I take this again. The activated complex is a transient state in which reactants attain after absorbing or getting the activation energy. Okay, so it's a quite simple concept. As I said, after they finish talking to each other and start dating, before they turn into fiancé and fiancée, there must be level of trust that must be built, and once that trust is built, the guy kneels down, sets forth a ring and says, "Will you marry me?" And the lady says yes. At that point, they are no more just reactants. They have turned into something else. They are about to get married, but they are not yet married. That's the same thing about the activated complex. It is about to become a product, but it is not yet a product. So the activated complex is analogous to the fiancé. Okay, so I could help out by drawing a particular table. It starts with collision, and after collision, you have absorption of activation energy, and then you have your activated complex. Now note, reaction has not occurred at this point. After the activated complex, you now get a product. Humans, the young guy starts by chatting or talking or whatever happens to start their whole thing, and after that they start building trust, which is the activation energy, and after they build trust, there's a proposal, and they are now at the fiancé level. Remember, as a fiancé, you are not married, so as an activated complex, you are not yet a product. It is a transient state. After the fiancé, we now talk about the marriage. So have this in mind, that the activated complex is just a transient state. It is that particular state in which reactants attain after they have absorbed the activation energy and they are ready to be converted to products. It's a very important part of this particular study, so have that in mind. Now, with this said, we would be getting into drawing diagrams, and these diagrams would help us understand the relationship between reactions and their energy. Now, there are two major types of energy profile diagram. The first one is an endothermic energy profile diagram. The second one is an exothermic profile diagram. Let's get to drawing. Now we're going to start with the endothermic energy profile diagram. But before we get to draw, note this. Endo equals positive enthalpy, which implies that heat of product has to be greater than heat of reactant. So put this down. Endothermic reaction equals positive enthalpy, which is equals heat of product greater than heat of reactants. Thank you very much. With that said, we now get to draw the diagram. So we have a diagram, and in this diagram, we have the energy on the vertical side measured in kilojoules or joules, and then we have a reaction pathway. Now let's get to drawing. Now, every reaction starts with reactants. So that means, before we get to that, I would like to give some values to this so we could get to understand. 5, 10, 15, 20, 25. These are just random values. So, but let's get to understand this. Now, every reaction starts with a reactant. So, we have the energy of the reactant in this particular diagram. Let's call this A colliding with B is 5. And then they begin to absorb activation energy, build trust, and then they get to what we call the activated complex. That's when they start thinking of converting. It's a transient state where after you get to that activated complex, you have your product. So it starts going down towards the products, and that's that. Now, please, I would like you to note something. For it to be endothermic, the product, okay, let's just use R here, P. The product has to be at a higher level than the reactant. That's what indicates endothermic profile diagram. The product, which is P, has to be at a higher point than the reactant. Remember, I told you guys that it starts with a reaction. So the reactant is what is going to start this particular trail. As it goes up, it becomes an activated complex, and then you have your product. But note this, your product for endothermic reaction must be at a greater level than the reactants in this case. So that's why we have the diagram like this. So with this said, we are going to now start to label. Now remember, I told you that the reactants would have to absorb a particular amount of energy. That amount of energy is what we talk about when we say activation energy. So that's that. The energy absorbed from reactant to the activated complex is referred to as the activation energy, in other words. So I have that this particular guy is labeled as the activation energy. That is the activation energy. Then we talk about this point, which is the transient state. This transient state is the activated complex. Activated complex. And this is the energy of the reactant, energy of the product. Then we have a final labeling here, which is the difference between the product and the reactant. When you are dealing with enthalpy change, we just mentioned, enthalpy change is equals heat of product minus heat of reactant. So the difference between the product and the reactant, what you have labeled here, is dH, which in this case is positive. Why is it positive? Endothermic is a positive enthalpy reaction in which heat of product has to be greater than the heat of reactant. Once the heat of product is greater than the heat of reactant, you have that the enthalpy change is positive. Now, I would like us to find exact values which would help us understand this the more. Let's say we are looking for the enthalpy change of this particular reaction. The enthalpy change of this reaction. How are we going to get the enthalpy change of this reaction? Quite simple. dH is equals heat of product. Now let's trace this. This is the product, this is the reactant. So the heat of the product is about, it's greater than 10. Let's just call it 11. So it's about 11 minus heat of reactant. The heat of the reactant is 5. So what do we have here? 11 minus 5 is going to give us 6 kilojoules. So is this positive? Yes. What made it a positive endothermic reaction, or what makes it a positive energy profile diagram? Because in the diagram the heat of product was greater than the heat of reactant, which is for endothermic. So please don't mix it up. Whenever you are drawing for endothermic, have this thing in mind. For endothermic reactions, the energy profile diagram has that the heat of product must be greater than the heat of reactant for this reaction's enthalpy to be positive, as we have proved here. Now, imagine you are asked to find the activation energy. If you are asked to find the activation energy, it is quite simple to do that. And how do you find the activation energy? Quite simple. Activation energy is equals the energy of the activated complex minus the energy of the reactant. I take it again. Activation energy is equals the energy of the activated complex minus the energy of the reactant. So in this case, what we are going to have is activation energy. Where is the activated complex? Is here, right here at the tip. That's activated complex. And with that said, as our activated complex, we are going to have that the energy of the activated complex is giving us, let's say it's between 20 and 25, let's just give it 22. These values are not necessarily very accurate, but in your graph, they are going to come out very accurate. And then the energy of our reactant is 5. So whenever you are asked to find activation energy is equals energy of activated complex minus energy of reactant. So what do you have? 22 minus 5 is going to give us what? It's going to give us 17 kilojoules. And that's your answer. So you have this in mind, that whenever we are trying to describe these processes, endothermic energy profile diagram must have a positive enthalpy. For you to achieve a positive enthalpy, the product must be at a higher point than the reactant. That's why when the reaction starts, it starts with the reactant, gets to the activated complex, and then turns into a product. And how do we get there? The reactant has to have a lesser energy than the product if the enthalpy change, which is labeled between the heat of product and the heat of reactant, is going to be positive. So with this, I hope you've understood how to draw this for your positive enthalpy change. Now, I could allow you could try the exothermic, try drawing for the exothermic, but I'll have to do that myself. Okay, now having said this, we are going to try the diagram, or putting down the diagram for your exothermic energy profile diagram. So, whenever you are dealing with an exothermic process, the enthalpy change, dH, must be negative. And if you are going to have a negative enthalpy change, what did we say? The heat of reactant must be greater than the heat of product. It's quite simple, so put it in your head. Endothermic has positive enthalpy, which implies that heat of product must be greater than heat of reactant. You know the basic reason is because dH is equals heat of product minus heat of reactant. So when you have the heat of product greater, you have a positive value. If the heat of reactant is greater, you have a negative value. So put that in your head. Now with that said, what are we going to do about this? Now we start with the vertical side. Okay, I think our marker is fading. Let's switch that. As I said, you start with the vertical side. And in this vertical side, you are going to have your energy. And then here you have your reaction pathway. Let's give this a unit, kilojoules. Okay. And then I give it actual values. Let's give it 5, 10, 15, 20, 25, 30, and so on and so forth. So let's get to drawing. Remember we said that if it is going to be exothermic, the heat of reactant has to be higher. So we are not going to start at the least value. We have to take it up a little bit so we could have somewhere to place the product as lower. So we could start here. Every reaction starts with a reactant. So just know that once you are starting is the reactant. Now it goes up 35 and this is 40. It goes up, gets to the activated complex, and then it starts going down to form the product. So notice something now. In this diagram, the reactant is at a higher energy than the product. It must go in this particular pattern. where the reactant starts and it ends up at the product. But for exothermic, the reactant is placed at a higher position than the product. This is what will lead to a negative enthalpy change. Okay, so with this said, what do we have? Activation energy is the energy between the reactant and the activated complex. So don't get it mixed up. It's not between the product and activated complex. Neither is it going to be between the reactant and product. It is simply between the reactant and the activated complex. That is what gives you your activation energy. So we have this arrow between the reactant and activated complex as our activation energy. But when you're now dealing with this topmost part is what we call the activated complex. As I said, it is a transient state after which the product is formed. And the energy that is absorbed for a reactant to be converted to an activated complex is what we refer to as the activation energy. Now, once this happens, we have that the product is formed. But then, don't forget this little piece of information. The difference between the heat of product and heat of reactant is what gives us our enthalpy change, which in this case must be negative. For us to be able to get the enthalpy change, first of all is that you need to understand that enthalpy change of any reaction, the H, is equals heat of product minus heat of reactant. I take it again. Enthalpy change of any reaction is equals heat of product minus heat of reactant. And having said this, how are we now going to get? Look at this diagram. It has our values labeled. What is the heat of product in this diagram? Tracing it is not an actual correct sketch. It's just a rough sketch. So let's say it's 10. So the heat of product is 10 in this case minus the heat of reactant, which is way up here as 20, would give us minus 10 kilojoules. So you notice something. Enthalpy change is equals minus 10 kilojoules simply because the heat of reactant was greater than the heat of product. So this is proven. Now, if you are asked to find the activation energy is giving us the difference between the activated complex and the energy of the reactant. So I take it again. If we are to write down our formula for activation energy is the difference between the energy of the activated complex and the energy of reactants. Okay, I'm going to let you put this down. You have the H is equals HP minus HR. And now the H is going to give you 10 minus 20 because the energy of the product is 10 as we found out, and that of the reactant is 20. Once that difference occurs, you have your answer. Minus 10 kilojoules indicating exothermic energy profile diagram. I hope this is understood. Now, how do we find the activation energy? Activation energy, as I said, is energy of activated complex minus energy of reactants. What is the activation energy going to be? First of all, in our diagram, if you look closely, the energy of the activated complex is there's a tiny 40 here. I don't know if you could say it, but yes, there's a tiny 40 here. So just have this in mind. Let's relate or say that the energy of the activated complex is 40 minus what is the energy of the reactant? The reactant is at 20 kilojoules, so minus the energy of the reactant 20. So what are you going to have as your activation energy? It is going to be equals 40 minus 20, which is equals 20 kilojoules. So quite simple. So a little recap to what we have said. First of all, collision theory. Collision theory states that for a reaction to occur, those reactant particles must collide. But for that reacting particles which collided to give a reaction, we would need activation energy. Activation energy, as I said, is defined as the minimum amount of energy required for a reaction to occur. And having attained that minimum requirement, something else is needed. What do we need to understand about that minimum requirement is that it can either lead to the production of an endothermic reaction or an exothermic reaction, which gives us two energy profile diagrams. The two energy profile diagrams are the endothermic and the exothermic. Exothermic reactions would have negative enthalpy. which implies that the heat of the reactant must be greater than the heat of the product as seen in this diagram. But for your endothermic reaction, it requires positive enthalpy, which implies that the heat of product will be greater than the heat of reactant. Do not also forget that when you are looking for the activation energy, it is mathematically given as activation energy equals energy of activated complex minus energy of reactant. I hope with this video you've actually learned something about how to draw the energy profile diagram. Thank you very much for watching. Remember, this is Wits Lounge, learning made easy.